Welcome back. Today we're going to expand on the basic idea of probability to talk about probability distributions. This will allow us to shift from the question, how likely is this one outcome compared to everything else, and instead ask, how likely are an entire range of outcomes on a variable with a common distribution pattern? It's possible to do that for discrete population variables by estimating the probability of each individual value. But what if we have a truly continuous variable? Or we need to know the probability of a value being above or below a certain criterion value. For that, we need to use probability distributions. The major intuitive shift here is from thinking of probability as a count, and instead moving toward thinking of probability as an area. And since we can both calculate the area under a standard normal curve, and we can standardize a distribution by converting raw scores to z-scores, we're capable of computing the proportion of the area, that is, the probability of a distribution to the left or right of a given value. The full equation for the area under the normal curve requires some complicated algebra or calculus, but handily we have both software and tables that can tell us the proportion of all the scores above or below a specific z-score. So if you've got a statistics textbook in hand, they're usually either in an appendix or on the inside covers. Look for something titled z-distribution, standard normal distribution, or critical z-values. The tables may be organized a little differently, but they all have the same purpose. All you need to know for now about what's under the hood, though, is that it's built on what's called a probability density function. A probability density function allows us to calculate the probability of a given value of a normally distributed variable falling within a certain range, as long as we know the mean and the standard deviation. We'll see later it's also possible to adapt this to deal with skewness, kurtosis, and other kinds of non-normal distributions. Unlike discrete event probabilities, the counts we worked with before, you can't estimate the likelihood of getting an exact value because the function is a smooth curve and an individual value has no width and so no area. So let's start. I'm going to draw a diagram of a standard normal distribution. Approximately. You can forgive my art. All right. So here's a standard normal distribution. The mean is 0. Standard deviation is 1. So if we ask, what's the probability of a score less than 0 on a standard normal distribution? The answer will always be 50%, or 1/2. If we look here, the mean below is exactly symmetrical to what's above. They're perfect mirrors. So tables will often admit negative z-scores, trusting that as clever statistics students, you're capable of switching the sign and looking up a positive value if you see a negative one. But as important as knowing what the center of our distribution is, what we really want is to be able to specify a specific point on the distribution and estimate the proportion of the total area under the curve that falls above or below that. To do that, we would use our table to look up the area between the mean and the z-score of interest. For one standard deviation, so z plus or minus 1, the table would tell us that the proportion of cases between that and the mean is 0.34134, or 34.1%. To figure out the probability of a score below z equals 1, we would add that number to the 50% on the other side. So if I'm shading this, here's our 34.1% between z equals 0 and z equals 1, but we've also got this other 50% over here we need to add to it to get 0.84134, 84.1%. If we wanted the smaller end of the distribution out here, then we'd subtract that distance from this distance from 0.5 to get 0.5 minus 0.34134 is about 15.9%, or 0.15866. You could also subtract this whole amount, if you knew it, from 1. Now, we can describe this result in two ways. One emphasizes the distribution, one emphasizes the case. First, the distributional. We could say that about 15.9% of values are expected to fall more than one standard deviation above the mean in a standard normal distribution. Alternatively, describing it in terms of case probability, we could say that a randomly selected case has a 15.9% chance, or a probability of 0.159, of having a value more than one standard deviation above the mean. They mean the same thing, but one emphasizes the fact that we're talking about the area within a distribution. The other emphasizes the fact that we can use this to talk about the chances of cases falling in specific areas. What if we wanted to calculate the probability of a case falling between two values? So for example, between z equals 1 and z equals -1. I'll draw another standard normal curve here. Got a mean of 0, standard deviation of 1. So what we want is, we want this amount that we already calculated. This is the 0.341. But we also want this amount here. We know that's also 0.341. And so we can either add these two together if we know both of those, right? Or if they're both on the same side, say 1 and 2 standard deviations above the mean, we can subtract the area of the 1, the area between the 0 and the larger 1, or between the left or right end of the distribution and the larger one, from the smaller one. So if we're doing z equals 1 and z equals -1, we would subtract the area above z equals 1, the higher one here, from the area above the lower one. You notice this area would be larger, right? It would be 0.68 larger, which is the number we're looking for. If we were to add those two together, we already knew that. So there are a number of these areas that are useful to memorize, though, at least approximately, because they're commonly used and they can give you a way to rapidly approximate probabilities. We did this, I looked it up in the table already, but I also know, and you should know, that specifically 68% or so of cases, 68.26%, fall within one standard deviation above or below the mean. That's what we saw here. 95.44 fall within 2 standard deviations above or below the mean, this area, and 99.73 fall within 3 standard deviations. That is, you have about a 1 in 400 chance of being more than 3 standard deviations away for a random case in a normally distributed variable. Now, if you wanted to find the probability of being outside that plus or minus range, for example, if you were looking for outliers more than 3 standard deviations away, you'd subtract that probability of being within a range from 0. So, as I said, if 99.73% fall within 3 standard deviations, then that leaves 0.27% that don't. To find the probability of being between the mean and a z-score in only one direction instead of both, if you know those standard numbers, the 68, 95, 99%, you would divide by 2. So 68 divided by 2 is 34, which is what we had up there. Or you can look it up in the table. And to find the probability of being above a given value or below a given value, look up the z-score in the table of the standard normal distribution and then adjust as necessary. If this sounds complicated right now, though, don't worry. It'll become second nature to you soon enough. The point is, we can use what we know about the standard normal distribution and the area underneath it, together with these tables, to estimate the probability that a case will fall within a certain range of values, if we've standardized it to z-scores, or to estimate the, the proportion of the distribution that will fall between those values, if we want to think of it in terms of distributions. Don't worry for now. Keep watching. We'll build on this as we go. Thanks for watching.